Sup y'all, it's your boy XX Seneca XX with the last video of FRQ Set 5, which is question 5. Let's get started. Here's a common physics laboratory exercise with data of an experiment provided below. Using the data provided, generate an appropriate graph that is associated with Hooke's law. So, we'll leave the graph to the side. Okay, Hooke's law is force equals spring constant times the distance the spring is stretched or compressed. Okay. So we're supposed to generate an appropriate graph. So we use the axes. Y-axis will be force in newtons, and the x-axis will be the distance in meters. So I'm going to plug these points in. 1 Newton, 2 Newtons, 3, 4, 5. And then I'll use 0.025, 5, 0.075, 0.1, and 0.125 meters. Okay. Next I'll plug these points in. This is about what the graph should look like. It's pretty much a linear line, and that is it. Okay. Part B, determine if the experimental data follows Hooke's law. Hooke's law, as I said before, is F equals Kx. And when you cross out K, because it's a constant, you'll find that F is directly proportional to X, which means when X increases, F also increases. And this linear line shows that direct relation, and therefore the experimental data does follow Hooke's law. That's part B. That's part A. Okay. Part C. Part C asks, if an 0.8 kilogram mass is used, how far will it stretch the spring from its initial resting position? Alright, let's draw another spring with the mass of 0.8 kilograms. The only force acting upon the block and that causes the spring to stretch is F of G, force of gravity, pulling the mass downwards. So how do I find the F of G of 0.8 kilogram mass? Just simply, F of G equals mass times gravity. Mass is 0.8 and gravity is 9.8. And we get 7.84 newtons. Now we can set up Hooke's law to find the distance stretched. F equals Kx. F is 7.84. K. To find K, we can use one of these other points using Hooke's law, because K is always constant, so we can find it using one point of data. So F in this case is 0.98 equals K, and X is 0.025. And we end up getting K equals 39.2 newtons over meters. You can plug that back in to here. 39.2 X. And we can isolate for X to get 0.2 meters as our X. Now, part D. Refer to the second data set, 0.1 kilograms, 0.98 newtons, and 0.025 meters. Now, if the 0.1 kilogram mass is stretched an additional length of 0.082 meters, which means it is stretched this much, and that will be our X, and then released, used energy conservation and calculate the speed of the mass the instant it reaches the equilibrium position. Okay. So using energy conservation, it's the spring starts out stretched and not moving, so we'll use PE string. And at the end, it reaches its equilibrium position, which means there's no more potential energy, but there is a speed, so therefore there's a kinetic energy. The potential energy of the spring formula is 1/2 kx squared, and kinetic energy is 1/2 mv squared. So we can cross out 1/2 since it's on both sides. K is 39.2, and x is 0.082 meters squared equals mass is 0.1 v squared. Multiply these two together and we get 0.264 equals 0.1 v squared. Then we isolate for v squared by dividing 0.1 on both sides. We get 2.64 equals v squared. Square both sides, we get v equals 1.62 meters per second. Part E. Instead, the mass is stretched an additional length of 0.164 meters, twice the previous length, and calculate the new speed at the equilibrium position and clearly state the relationship between the distance stretched x and a maximum velocity v at the equilibrium position. Okay, we will do the same formula. PES equals KE 1/2 kx squared equals 1/2 mv squared. Cancel out the 1/2. Spring constant is still 39.2, but the x is now 0.164 squared equals 0.1 v squared. Multiply these together and we get 1.05 equals 0.1 v squared. 10.5 multiply both sides by 10 equals v squared. Square both sides, we get v equals 3.25 meters per second. Now, when we compare parts D and E, when we double the spring length, the amount of spring we stretch, as we can see, the velocity also doubles. So, when the x doubles, v doubles. Based on this, we can clearly say that there is a direct relationship. Between the distance stretched and the maximum velocity at its equilibrium position. And that is all the parts. Hope you enjoyed this 5-video series. Hope you learned something. It's your boy XX Sonic XX. I'll see you in the next FRQ set.